Time travel debugging is a paradigm shift in the way you interact with the target. The ability to go back and forth in the timeline is already a bonus. The true capacity is where you can run queries. Let's say you can run a query to collect all of the time that a particular API function is called.
That shift from stepping through code to querying execution is exactly what we're exploring today. Welcome to Behind the Binary. I'm Josh Xusheng, and my guest is Xusheng Li, a developer at Vector35 who is currently building the bridge between time travel debugging and Binary Ninja. Xusheng has been recently finding ways to make time travel primitives more accessible for reverse engineers. He's used these techniques to solve some incredibly difficult puzzles, from hardware-level encryption to advanced malware. And today, we're breaking down how this tech actually works and why it is something you should be using. Well, welcome to today's podcast. Thank you for taking time to join me. And I think we're going to have a really interesting discussion around an area that I have been fascinated in for years, that is debugging. And I'm even more fascinated in, that is this area of emulation and tools like Time Travel Debug, which I think is a really interesting application of it. You're with Binary Ninja amongst many, many things that you're working on. And so that'll probably be something that we also talk about is the integration with BN, because I think it's a really fascinating part of adding to our workflows, the ability to go through a trace in a tool like Binary Ninja. So welcome to the podcast. I guess let's just start with debugging in general, because this is something that it's, when you look at like the RE tool suite, a lot of our tools have not changed much in decades now, and debugging is definitely one of those things. I mean, it's taken Microsoft years just to give us a fresh, clean WinDebug user interface. But TTD is one that certainly is different. It's a shift, I think, it's certainly a shift in how I've looked at debugging. Like, what have you seen in the debugging landscape over the years, and what do you think TTD? Maybe give us a little background on what TTD is. Like, where do you see that as like changing how we look at debugging and how we approach debugging?
Yeah. So, like Josh said, TTD stands for time travel debugging, and it's more just like we somehow record a trace of the program's execution and then replay it during debugging, and then maybe run analysis on it and gather whatever information we want from it. So the debugging landscape has pretty much been stable over the maybe 1 or 2 decades. It's like there has been no changes. People do debugging in the same way over and over again. And I do think time travel debugging potentially can give us a huge jump in our capacity in terms of debugging, because it has multiple advantages over traditional debugging. And we will get into this more as we talk over it. But just as a quick glimpse of it, so when we do time travel debugging, once you have the trace recorded, you have everything on file, and you don't have to worry about whether I click this button correctly, or maybe I step over this function or step into this function, or maybe let's say I had a fat finger and I just pressed the wrong button, or if let's say we're debugging something that is sneaky, let's say it's a malware and it downloads from the C2. Now I wouldn't be bothered whether my IP address will be spotted by the C2 server and be banned from accessing it again, right? So everything is scoped, is confined in this trace. And with this trace, you can replay and reconstruct the state of the program, like the register values and the memory values at every moment in the execution, like at every precise instruction. That is like potentially billions of instructions we're talking about, because the modern CPUs are very fast, and even if it's just a very simple program, it executes millions into potentially billions of instructions. So having everything saved into this one trace file and have the ability to replay it and do whatever analysis I want at my own pace with a easy mindset, I think this alone is already a lot better than trying to wrestle with a real malware that is executing on your machine. it's not necessarily a malware, just wrestling with a program, and that program might even try to actively counteract what you are trying to do. Anti-debugging is a thing, and there are all kinds of tricks that just making a debugging person's life harder. So
Yeah, and TTD. So when I first started, I'd heard of Time Travel Debugger, this concept years ago, and it just never got high enough on my radar that I sat down and figured out who was developing it. I think there is some capability in the Linux ecosystem, maybe GDB or one of those products. But Microsoft, I think, is really the only tangible option out there outside of just pure emulation, which I'd like to chat about at some point as well too. But it's also like, so I started getting into it, and then I realized like this Microsoft released this almost a decade ago itself. It was the late 2010s or something. I don't remember the exact point, but some of the early papers where they talk about the capture engine and the application, the technology, and I'm sure internally they had it. I assume they had it much longer than what was released to the public. So even this has been around for a while. Is there a reason, in your opinion, that adoption has been relatively slow? I mean, I still meet a lot of colleagues that don't leverage it, that don't utilize it. Product adoption seems to be slow, integrating it in tools like IDAs and the Binary Ninjas. Although Binary Ninja, we'll save that for the end. You seem to be, though, definitely on the leading edge of getting TTD integration done really well. So. Reason you see that adoption has just been slow with this technology?
I think, there are multiple reasons on this. So first of all, whenever something that is new that comes out, there has to be a gradual process that people adopt this. And this is not like AI. Like, this is not like large language model. You can talk about everything you think of with it, and it will just do it for you. This is like it's a big leap in our debugging capacity, but you think of how many people do reverse engineering, and inside of this small circle, like how many people are willing to try new things. Now, if you factor that in, it's actually a pretty small cycle. So, TTD is cool, but people fail to see its potential. And that is exactly what I'm trying to change, because I know this thing is cool, and I want people to adopt this new technology and integrate this into their reverse engineering workflow. So I recently gave a talk at the Reverse conference on the topic of breaking encrypted USB drives with time travel debugging. And what I gave the audiences two takeaways. Now, the first one is on the security of the drives. That is obvious. The other one is on adoption of TTD. Basically, that talk gives kind of like a step-by-step tutorial to the audiences. Basically, that talk gives the audience a pretty good idea of what can be achieved with TTD, and in the hope that they will see, with TTD, we can solve this problem much, much faster compared to traditional debugging, so that they can maybe give it a try. And also, that is the reason why I have been trying to adopt or advocate for the TTD integration inside of Binary Ninja. Because honestly, the Microsoft developers at Microsoft has done all of the hard lifting of creating this TTD technology, which we can also talk about a little bit, because that is really, really an engineering effort. So, but now the TTD, Winterbox TTD interface, although it's useful, it provides all of the necessary information for you. But you have to remember a lot of things in your mind. Like, you have to type that command dx dash whatever, to run a query, and it gives you results, and it's a command line interface. So that is not cool. I created a table where you can basically right click on this particular instruction or address, and then basically ask for all of the moments that this instruction has been executed, or all of the moments when this memory address has been read and read. Now, this is actually just a small step forward, but when people see this, they basically see, oh, I didn't know we can do this, and this is so cool. I'd say, well, this capacity has existed for many years, but it's just not adopted by people.
Yeah, I think that's a really important point because the commands, I mean, WinDebug, maybe that's been its Achilles heel for decades, and why people or folks in the industry just there seems to be a love or hate, maybe it's
Yeah.
for some people a love and hate relationship with it, but it's perceived as having significant learning curve. If you compare it to the history like Ollie debug and x64 debug, it's seen as more user friendly because
Hmm.
more of the interactions are done through the UI versus having to get into the command. And I would say TDD is no different, and that you do have to remember a lot of commands. And even as someone who uses it often enough, I forget them all the time. I'm constantly going to an LLM, which, by the way, LLMs are terrible at generating these commands. They oftentimes are just completely, at least in my experience, hallucinating the commands to use and the properties of the object model. So cheat sheets, I'm always going back. In fact, I have my own, like many WinDebug users, I have my own cheat sheet and tried to share that with resources with the community through some different blog posts and stuff as well. But I need these cheat sheets because I guess it's also like common Microsoft things. It's just not an intuitive. I mean, the commands get long; they get
Yeah.
hard to remember. So there is a little bit of a learning curve there, and the UI is still basic. Basic WinDebug. You're not going to really experience the full capability of a trace
Hmm.
through the UI. It is all done through the command line.
Yes. And I think, you mentioned LLM has difficulty of constructing a correct command or query for TDD. And that is also a perfect explanation for why people are not really adopting that. That is because it's so niche. Like, reverse engineering is already a very niche field, and time travel debugging is a very specific and advanced field. So it's even more niche than debugging. So that is totally normal that is not really widely adopted.
Yeah. So I think a mistake. I know a mistake I made when first looking at TTD was that I saw it as just an opportunity to take my normal debug habits and be able to do them backwards. All right, we have a trace, we have the ability to go forwards in a trace, and then there's additional commands that are just the opposite of those forwards. So step into, step out. You have step backwards, step into backwards. And this is great. Like this in and of itself, I think is worth everyone checking out TTD because it can be an incredible time saver. But you have to look beyond that. The real power comes from having a database of execution data. And now you don't have to necessarily step through the program to understand what it's doing. You can query the object model and you can use these queries that we're talking about that are kind of cumbersome to build, but incredibly powerful because you just mentioned you don't have to go look at the position or the transition from code to code. You don't have to look for when does the code allocate a region of executable memory and execute some shell code so I can find the entry point. You can just query for it. You can find a region of addresses and say when is the first byte executed in this region, and there you go. And it's one query in order to do that. So I think that, and it sounds like you're really going to surface that through tools like Binary Ninja because that is really where the power is at, I think, with this technology.
Yes, exactly. So one of the important messages I try to convey to the reverse audience is that time travel debugging is a paradigm shift in the way you interact with the target. As you said, the ability to go back and forth in the timeline is already a bonus, but the true capacity is where you can run queries. Let's say you can run a query to collect all of the time that a particular API function is called. Let's say we run a query on kernel32 create file A, then instantly we know maybe this sample opened 200 files, or let's say at least created 200 file object in its execution. This is impossible to imagine in traditional debugging because in traditional debugging, you have to basically put a breakpoint there and resume many times. And I guess if it's like hundreds of times, nobody do it manually. Now, of course, we talk about you can still use a script. You can do whatever automation, but that is not comparable to a one-stop solution with TDD, because you can also do the same with memory read and write. You can see how the memory is accessed. Like I can select a particular address and just ask, hey, give me all of the moments this address has been written to, and it will give me a list in Binary Ninja at least, and in a nicely formatted table inside of which every row represents a time step of an event, and you can see the time step value, the instruction pointer value, the memory access value, among other metadata. And also, once you double click on a particular row, you instantly time travel to that. So I'm really trying to make the experience more integrated and streamlined in Binary Ninja to make this tool more accessible to people, because that is one important factor to invite people to use it.
Is there so probably I'd say maybe one of the areas for anyone who's new with time travel debug is how the trace is deterministic and it is fixed. You're on a fixed path. So that's maybe one of the areas that can be a little surprising if you don't think about, or if you're just not familiar with how emulation and how the process that WinDebug is doing in order to capture the trace. You hit a conditional and you can only take the path that the code originally took. You can't modify that unless you go back and modify the binary and then capture the trace again. And like once you capture a trace or begin the process of capturing a trace, you're hands off. You're left to observe until the trace is captured. So that might be an area that is a little bit, well, yeah, it's a little difficult, especially as you're first getting used to working with trace files. Is there anything else that you've encountered that is surprising in how this technology is working, or limitations that you have found in working with it where there just isn't a good use case? Or I mean, you talked about finding a vulnerability in your presentation at Reverse. Could you maybe give us like a 30-second overview of what you did there, or how TTD helped you with that analysis?
Oh, so I found multiple vulnerabilities in some encrypted USB drives. Now, of course, interestingly, my research doesn't really do hardware research. That is not my field. I looked at the software that is accompanying the drive, and in many cases, let's say you want to unlock the drive, you provide a password, right? You type in the password, and usually you would expect that password to be sent to the drive for verification. But in my finding, in many cases, the correct password is actually sent from the device to the software for comparison. And that can be intercepted, because once something is in the memory, you can, of course, intercept that. But having a proof for that, or actually finding out how and where to find that value, proved a little bit challenging, or interesting task at least. And I use time travel debugging to help that. Basically, I can trace where this verification is done, and then from there I can see where it is coming from, and I have I can basically backtrack it to the moment where the packets are being sent on the USB.
Okay, yeah, I completely made that a huge ask. So, and a multi-part question, which wasn't fair of me. So if I go back now, maybe to add a little clarity with the the difficulties of TTD, maybe we could actually just take a step a little bit further back, because TTD is a form of emulation. How does it compare to other emulation tools that are out there? And there's a whole slew of them that have also been around for quite some time. Unicorn is probably one of the more popular ones. We have QEMU, Anger, Triton, and they all serve a slightly different purpose.
Mm-hmm.
But it seems like the one thing they all have in common is extensive buildup. The first time I started playing with the emulation framework, having not really understanding what I was getting into at the time, I didn't realize I had to allocate the stack space, and basically I had a blank environment in which I had to implement all the details. So if I was looking at a piece of malware and it wanted to interact with the operating system, I had to implement how it would interact with the operating system. I guess where do you see just the general emulation space, and where does TTD fit into this?
Well, that's a perfect question. So, so to start with, I think you went ahead and called TTD a form of emulation, which, in my personal opinion, I think that is not always true. So,
Mm.
TTD is, I would say, on its own, a new form of debugging between actual debugging on a real process or full emulation. I think it's something in between. And this actually comes to how TDD is implemented. So there are multiple ways to implement TDD, and we can start with RR. So for a general overview of how it works. I think a natural question people ask about TTD is how TTD is implemented. And we can actually have a quick overview of that. So I think one important thing I want people to know that TTD recording is not feasible with single stepping. So we all know that x64 debug and also GDB has one form of tracing, so basically execute one instruction and see what has changed and save it into the file and then continue doing that. But that doesn't scale. Like you can't really even try to emulate a program entirely, and you can't think about maybe recording billions of instructions. That will be terabytes or even larger data set. So that is not how TDD is usually implemented. So TDD takes advantage of a property of most instructions that is deterministic. Let's say we have a value in register REX and RBX, and now we execute an instruction that is XOR REX RBX. Now, if both of the values are known, and we know that the next executed instruction is this XOR instruction, we know what is going to happen. So this instruction does not need to be recorded because it is deterministic. And if we have a basic block that is entirely deterministic, and we have the state of the target at the entry point, then this entire basic block doesn't need to be recorded because we know what is going to happen. And this also applies to functions, etc., etc. So basically, we only need to record what is not deterministic. Let's say the program reads a file from disk, and that disk content needs to be recorded because that cannot be deduced from the program itself. Let's say you have the program, but you don't have the file on the disk. You cannot really know what is going to happen after this read system call, right? And also, for example, if the program does a CPU ID call, let's say if the program executes the CPU ID instruction, you might also want to record that because by the time you replay this, you are potentially on a different machine with a different returned value from CPU ID. So basically, the high level idea of TDD is to record anything that is not deterministic during program execution. Now, to be fair, this is actually a way too simplified version of how TDD works, and that doesn't. That is not even respectful for the Microsoft developers' efforts to bring this technology. But unfortunately, most of their engineering efforts are not available to the public. However, RR from Mozilla is actually open source. So if you're interested, you can either read their paper or check the source code to understand how TDD work better.
One of the many challenges with emulation is there's no framework I'm aware of that natively produces this sort of trace file. I suspect you could create your own, maybe LLM powered today. You could create one in short order, but then you are recording everything and all of the state changes and all the registers and having to determine what to capture, not to mention your interactions with the operating system. And so this seems like a massive undertaking to do that. And this really sounds like a clever way, because even with TTD now, if you're working with it, you'll capture a trace you'll create an index file to allow the ability to navigate that trace. And even small program executions can get quite large, even though they're performing these optimizations. So this is really a great application with the technology. Have you found then, so you're integrating it programmatically, have you found it to be straightforward to work with? I imagine you're using the debug engine, just the DLLs provided by Microsoft, in order to kind of tap into the TTD ecosystem and load up trace files and begin integrating it into a product. Have you found that to be a straightforward exercise, or is it challenging? I've looked into it a little bit myself, and it seems like the lack of documentation is usually the primary hurdle.
So I think, to be fair, the debug engine API is elegant, but that doesn't mean it's obvious to work with for people like me that doesn't work at Microsoft. Because, as you said, there is no documentation, and also, honestly, WinDebug is like the only one that consumes this API. So I did actually run into a lot of challenges when I tried this. And you can't, I still remember the excitement I had when I made the TTD work inside of Binja for the first time. I basically just created a new debug adapter. The debug adapter is the way we call some piece of code that actually handles the debugging. So with debug engine, we have a regular debug adapter that is for regular debugging, and also we have a TTD adapter. So it is not a lot of code, because most of them are shared with the ordinary debug adapter, because the way you read memory, you read register is the same, but the way you load up the trace and also just have it be able to work is, I still feel proud of that, because without any documentation, I figured out the way. Now, of course, as I move deeper into this, I emailed the developer of Microsoft, and they responded, and we communicated over email, and over the time we also had some meetings to basically just discuss what is the correct way to do things. They gave me a lot of advices, and I sometimes even ask them, hey, you guys should fix this bug. This is killing our integration and it doesn't work. And also I gave them many bug reports that are previously not seen by them, because for one interesting example is the WinDebug debugging. A particular aspect of WinDebug debugging would totally fail if you're using it on a machine with no network interface. Now, I'm not talking about having internet. I'm talking about the fact that it doesn't have a network interface will break it. And that is what exactly my reverse engineer is trying to, because when they spin up a malware analysis virtual machine, they naturally do not really attach a network card to it, right? Because for all good reasons. And that is exactly what is happening to the Flare VM. Is like our debugger in the beginning doesn't work, and they say, well, why do you need internet for debugging? And I say, you don't need internet for debugging, you need a network adapter for debugging. That's funny.
Yeah, that is funny. That is a side effect I would not have anticipated during my debug session. And to me, that brings up an interesting point, because I've come across this a couple times in my career now, where tools and sort of techniques that I've used and relied upon very heavily for malware analysis and reverse engineering activities, you come to recognize that the folks behind those tools they don't really consider the RE community one of their primary targets. And I suspect that WinDebug and Time Travel Debug is certainly one of those technologies where, yes, maybe it is there for vulnerability research. Maybe it is more for, and likely more for just troubleshooting actual bugs. I was a little surprised when I started digging around the different components of TTD to find the command line trace capture utility, TT Tracer, is just available in System 32. So it's there, I believe, now just by default with Windows. So it seems like then the actual reverse engineering community, those at least focused on malware, maybe aren't a big consideration in how this technology is being developed and looked at. Have you seen that? I mean, has that been
Yeah.
an experience that you've had, at least with TTD in this case? And I don't mean that as a negative thing. It's just sometimes it helps me to better understand why the technology hasn't adopted as well as it has, or maybe why there's certain features that are lacking or just bugs that are present, is because I continue to live in that very niche region of users that are very niche about the things that they
Yeah.
use.
I think it's totally fair. Like you actually had a great observation. So TTD, when it's originally created, is more like a tool to help software development. Because you think of RR is created by Mozilla for debugging complex bugs in Firefox, and WinDebug is essentially, and its TTD solution is essentially created as a way to help developers. And interesting, so I also use TTD to troubleshoot bugs in Binary Ninja itself, because I am a Binary Ninja developer and Binary Ninja has bugs. So I also use TTD to get recordings of execution and debug it. And it's interesting. So in one of the cases where a user reported a crash, and we spent a lot of time debugging that, and there is no outcome. And I just asked a TTD trace of the actual crash, and the user is able to get that for me. And I see that crash is happening on a particular instruction that, according to the specification, shouldn't be triggering a exception at all. And it turns out that the user is actually having a faulty Intel i9 CPU, which is the incident happened a while ago. It's basically for certain CPUs, there is a bug in your CPU, and there is no issue with the Binary Ninja program. So once the user updated the microcode on that CPU, the bug is fixed. So I think that is one of the cases where I used TTD to solve a mystery that would otherwise be very hard to pinpoint. So on this front, I think most of the developers behind the TTD technology or the solutions are treating the developer, software developer, as their primary targets. I think most of the developers of TTD solutions are considering software developers as their primary users. And us, reverse engineers, is some nice addition, probably. Because you think of how much value software developer generates in terms of money, and how much value in terms of money reverse engineers can produce. I'm not saying reverse engineer is not important. It's of course very important, the price and the security of the nation and of the world. But you just think of the amount of money, then that is not comparable. So I'm happy that these developers, when I reach out to them, they are happy to admit this is an important use case of their solution, and be happy to work with me. So Binary Ninja actually has the integration with multiple TTD solutions. It's not really limited to WinDebug. It also has RR integration, and also Undo integration, which is a British company, and also another one from Europe is ES-Riven, is a full system one based on QEMU. These are all great, and what I want to do is basically to have Binja become the main hub of TTD. So whenever you think of TTD, you think of Binja. That is how I envision we're going to win some users, because if we have integration with multiple solutions, or better say, we do better than our competitors, we just become the natural choice for people.
Yeah, and I think this implementation of this technology is just as you described that scenario. I mean, that's a great, maybe not necessarily an RE scenario in this case, but just the ability to troubleshoot something, to share. I mean, you think about, RE work tends to be solo work. It's not inherently very collaborative, but even when I do, I mean, because you'll always run into samples that you just can't quite understand. You can't quite figure out what it's doing or what you're missing. I mean, and that's kind of the inverse of software development. I spent years doing that, and there was times where I just couldn't quite see the bug in my software because I needed that distance from it. I needed somebody else to look at it, and so capturing these traces and sharing them, it's just a great opportunity to say, here's what I'm looking at, and here is the exact same trace that I'm looking at. You don't have to go and capture it yourself.
Yes,
we can synchronize on the same exact thing, and bringing these different things under one tool, that just to me feels like a very natural evolution and a much needed one too. Getting the tools to have more than just I expect every version of these tools to be a little better at generating pseudocode and a little better at disassembly and a little better at being quick to load a project, but still version to version they're not fundamentally changed how I interact with them and how they operate. And this is definitely something that is changing how I look at reverse engineering. So that's great.
One of the things I was thinking about doing it, or at least motivated in doing, is the motivation is debugging is a delicate process. You think of we have lots of malware from the past, and potentially on the scale of millions or more. You think of that, how many of these can still be executed properly as of now? Does a malware from 10 years ago can still be executed properly? That is questionable, because and of course we can still load it up in Binja and analyze it statically. But if the C2 is gone, then it may not really run. So a project I wanted to do is basically we should create a data set of TDD traces of malware. And this can be used for researchers in the future, because once you have this trace, it's sealed. And no matter whatever changes in the future, you can still come back and analyze this trace and apply whatever new technology on this trace and see what you can get.
And because you have with TTD, as you mentioned earlier, you have memory, you have network capture. So if it has the full access to the resources it needs through the operating system, it does. I mean, I think it's just, even for me, it's a great triage tool. On the occasion that I get something that I want to analyze, and I suspect or I know that it's a downloader, or I want to see some C2, or maybe I just don't know. Like, if I have the ability to let it connect to the internet, grab a trace early on. It's not going to always be perfect, right? There's plenty of flaws. I mean, we're describing this technology as something that works well and it's this ideal thing, and it's not. Right? I have had plenty of issues with traces. I've had derailments and just things get out of sequence and gaps. maybe the gaps are inherent because it's just part of how it's recording. Sometimes it's hard to tell from my usage. But you can get that capture right away, and then you have it. And then if the C2 goes down later on, or you can't fetch that secondary payload, well, now it's hopefully in the trace, and you can extract it, dump it to disk, and analyze that as an individual thing. Not to mention, now we have this trace file, and how do you integrate with that? How do you there's some projects out there that allow you to apply Yara to the trace file and other things. And I think Kappa, anyone's familiar with Kappa, like Kappa seems like here's a great example of extending a Kappa tool to say, okay, now because that's all Kappa does. It looks at capabilities, it looks at heuristics and signatures and APIs. Well, now we have a trace, and so maybe we have a little bit better visibility because we can see through the runtime linking, or we can maybe see through layers of decryption and deobfuscation. Now let's look for a query, observe those same API calls and those patterns, and get capabilities out of it as well. So it just seems like there's a lot of great opportunity here.
Yes, of course. So I think I actually talked with Willie formerly from Mandiant, or better just say, I have talked with Willie on this topic a lot, which Willie is a maintainer of the Kappa project. So we talked about how feasible it is to have a TDD backend for Kappa. Now, so Kappa has IDA, Binja, and Ghidra backends, along with a few other things. we talked about whether we can have a TDD trace as a backend, because you think of this, Kappa is detecting the capacity of the program. Now we have this trace, and for example, we can of course extract all of the API functions that has been executed from the trace, and that is actually one feature that we extract from the binary in the static analyzers. And one advantage of using the TDD backend is, let's say, I think with one problem with Kappa. No, I'm saying Kappa is great, but one problem with Kappa is whenever it says something, it screams. Let's say the binary has a call to its debugger present, and it may actually just call it out and see this binary has the capacity of detecting a debugger. Whereas what is actually happening is this is just part of the C runtime, which doesn't mean this itself has the intention of detecting a debugger. Now, is a TDD trace, you would not be bothered with this because you would have a concrete execution of the binary, and whatever is extracted from the trace is true, is true behavior. So you have maybe less false positives in terms of this. Now, of course, we have other problems like coverage or whatever, but this is just saying that if we have a TDD backend for Kappa, it's going to have less false positives, and it is not really bothered by packing or whatever things like this, because the concrete execution just removes all of these stuff.
Right. Yes. Yes. And you're getting runtime information, which I think again is just it's a great visibility. It's a problem with a lot of static tools and a lot of static approaches I see is that what you encounter, and I guess the terms and the techniques are very muddied, at least from my viewpoint these days. And 10 years ago, you could say, oh, there's just going to be a layer of packing, and it's going to unpack, and you just have to figure that out. And you can kind of reliably get to the next stage. Packing is still definitely a thing, but then there's all kinds of techniques now to modify the binary and to add layers of obfuscation, from the compiler to post binary rewriting and builders and all this stuff. And so it can get really Chris, can get really challenging. But a lot of approaches they just ignore that problem because it's hard to solve. You give a binary, let's say you don't have a lot of experience, you give a binary to Kappa and it's obfuscated. Well, it's not going to look like it does a whole lot. But now you give it a trace, and assuming you get a good trace. What is a good trace? Well, you don't run into any inherent anti-debug, and you're able to maybe allow it to connect out to the internet and a few other things. And now you have execution, and it's noisy, I guess, in a way, but what are your alternatives? You go into a VM, you start a procmon, you get a procmon dump, or you go to a sandbox and you export some JSON. Like this is the truth. This is the ground truth of the execution. And so it's again just it helps to at least maybe see past some of those layers of obfuscation with tools that traditionally are going to have a problem with it and require you then as the RE or the analyst to manually deal with it, right? If you want Kappa to statically analyze a binary and it's packed or it's obfuscated, well, then you have to move past those layers in order for Kappa to help with your analysis.
So I think my take on this is TDD is bringing much tighter integration with multiple tasks and workflows. So still taking your packed malware example, I would say analysis sandbox are very useful, and it should definitely be used in the future, still used in the future, even if we have TDD. But you think of this, the malware analysis sandbox will only tell you what happened. It wouldn't tell you how it happened. Let's say a file has been encrypted. You didn't really see how that happens in real time, but with TDD, you can basically put, first of all, find the right file call to that, and then you can tint the buffer back and all the way back to the crypto functions on how it happened. And then from there, you can see whether the crypto system is secure. And that also then goes back to, sorry, I'm just trying to keep mentioning that my reverse talk, because that is how exactly I break one of the crypto system that is used by a encryptor utility that is coming with the USB drive. So now you think of this, you have a report from the analysis sandbox. It wouldn't really be easy doing all of the following up work, right? Now, of course, if the report already solves all of your problem, then perfect. You just write your report and put that report in your report, is done. But what if it doesn't, right? You are fighting with a much more complicated malware.
Yeah.
So that TDD brings a lot of different workflows together, like basic triaging to all the way to advanced analysis. This is also beneficial because I think, at least honestly for myself, like if I have to use a dozen of tools to do my work, I feel dizzy. I don't know how you feel about it because you're more professional on this. Like, how do you feel about this?
Yeah, multiple tools. Yeah, definitely. I think that's one of the challenges that has always been there is just the constant bouncing around and a little bit of context switching that goes along with it. Yeah, I mean there's constantly, and I'm not saying that like WinDebug now is the solution for all my reversing needs. It certainly isn't, but it does seem to bring together a lot more of those workflows from the triage to the invasive. And so if you have something like a trace, you have that ability because you're going to get, if you look at a Procmon capture, Procmon's giving you some APIs to give you some insight into what was modified on the system. Well, you can do that same thing with a trace. You can say, well, I just want to look for APIs that generally would indicate a modification to the system. And then, like you said, if you need to go deeper, if you need to actually figure out, well, how did they implement the crypto? Well, now you have all that there as well. Whereas Procmon, that data is gone. And same with the sandbox. Sandboxes are great. They have been crucial for analysis for my entire career, and I expect they will be for the future. But it's a data problem. They can only capture so much information. They can only give you so much information, at least on the free tiers. I suppose a lot of times if you upgrade and pay, you get a little bit more insight. I've tried running my own sandboxes, Cape and Cuckoo, over the year, and kudos to anybody who's got those up and running and fine-tuned. They're incredible projects. The maintainers make them as straightforward as possible. I know they do, but they still take time to build the VMs and network everything and keep everything up and running. So.
Yeah, I think, so I just had an idea when I listened to what you said. Basically, so I think TDD solves the granularity problem because it captures every detail, and now you can decide whether you use a microscope to look at it or you look at it normal way. Because you can just look at all of the called APIs, then that is a very high level overview of that. But you can also just then take a microscope out and dig into the particular instruction that is happening. This is not really possible with either sandbox, emulator, or debugger because you have to decide the granularity problem ahead of time. You can't really make decisions later. Now this just reminds me of some of the recent advances in photography, because basically you can capture a picture and adjust the focal length later on. Basically you want this guy to be clear or the guy in the background clear. You don't have to really decide that when you take the picture. You can have the freedom to modify that later on, which I think is great because preserving more possibility at the time. Preserving more possibility for later is better, is where TDD is better in this sense.
This is maybe a big area, but two things are still on my mind, and they're definitely related. One is just the future of debugging. Do you see this being that path? And then the second area that I was hoping to get your opinion on is just, where do you see LLMs fit in this space? I have my opinions and stuff, but certainly there isn't a rush to MCP all the debuggers out there. And
well, you mentioned the future of debugging, and I feel that is carrying a lot of weight. That is not something for me to decide. It's like you bring up this big word, and I'm instantly devolved. But I think I'm actually trying to make the future of debugging brighter. It doesn't mean I will try to solve this problem, but I do want to provide my contribution to this part of reverse engineering. And I do think TDD is going to be playing a crucial role in the future of debugging. Potentially, let's say maybe 5 years from now, when we talk about debugging, we will also just by default go to TDD. It is only like when TDD doesn't work, people talk about debugging, and maybe by that time, debugging is more like a mystery, and you come from a wizard school, you know how to debug yourself. It's just like maybe you can write assembly languages and assemble them to hex That is, because the technology is also like we build more and more abstractions based on the previous things, and it becomes more and more capable, and the lower level things is becoming more practiced less and less. So if I would say so in my personal workflow as of now, I always try to use TDD whenever I can, because there is just no reason to do traditional debugging for most of the task. So basically, I think I want to see a world where when people talk about debugging is time travel debugging. And also, so another part of my vision for TDD and also the future of debugging or even program analysis, well, that is a big topic, is basically you can think of TDD as a form of data flow analysis, or at least it supports a data flow analysis, because you can see this buffer is here, and you can see where it goes to and where it comes from. So with traditional debugging or traditional analysis tools like BinaryNinja or Ghidra, we're focusing too much on the code, which is the code flow. Now, of course, the code flow actually can help you solve the problem, because that is how reverse engineering has been done in the past 2 or 3 decades. But you think of that, this is actually sometimes indirect, because you look at the code and you deduce what happens with the data. Why not we just see what happens with data and maybe build let's say with TDD, we build a temp tracking engine that will basically automate all of the data flow analysis that has to be done manually by now. So, and that is also one thing I wanted to build for Binja, is basically you can automate a data flow analysis, and that is concrete data flow analysis. It doesn't have path explosion. It doesn't have many problems it doesn't have path explosion. It doesn't have a lot of hard problems with static data flow analysis, which we know is a nightmare. But this is concrete data flow analysis. Is, I think, at least a order of magnitude easier. So putting this together is basically we're having a new way of looking at debugging. Is basically we track the data instead of the code. Now, taking your case as an example, like when we unpack, we actually care about the code less than the data, because the data is, by data I mean the code that is eventually written to the memory and later executed. We don't really care which compression or encryption method is used. We care about this buffer, right? And in my recent research is also we care about this key, where it is coming from, where it goes to. So that is an important way of looking at debugging, I think, which I'm also learning myself. Now, I might have some visions that is good or maybe ahead of some of the folks, but I'm also learning this because this is just like a totally new world. Like TDD opens up a new world for all of us, and there are a lot of things to explore.
Do you have any, your thoughts on what role does AI play with debugging?
So I personally think, and also discussed with our sidekick team, is basically TDD is more suitable for AI integration compared with regular debugging, because regular debugging is like a open world exploration. Everything can happen. A lot of uncertainties, but with TDD, everything is fixed. It's inside of this trace, and it's going to be pretty secure. Like, you don't really expect something to jailbreak your LLM just by analyzing a trace, but that can happen with real world debugging. So TDD is suitable, but it's also challenging because we will be facing a different problem that has never emerged before. It's like we have lots of information. We have states of the target at every instruction. The LLM can potentially be lost. And there is no way to predict what is going to happen before we actually have. There is actually no reliable way to predict what is going to happen before we actually hack up a POC and see how well it does. I envision it can actually solve many of the easy to intermediate level problems, because here is a trace and he knows how to interact with it. We would reasonably expect it to be able to solve certain challenges or certain problems, So with access to the trace and the ways to interact with it, we would be reasonably confident in its capacity to solve many of the problems. But that is not really going to say it can do everything, because even with the trace, there are still a lot of hurdles in analysis, and I believe AI is going to be helpful in this, and I'm really looking forward to that.
I think we'll call it an episode. So thank you so much for your time and joining me today. We had a great conversation, and really enjoyed chatting with you. Any final thoughts or anything that you'd like to say before we hit end?
Thanks for hosting me, and thank you for all of the audience for following through. And I hope you enjoy reverse engineering with TDD.
And that's all for this episode of Behind the Binary. Thanks so much for tuning in. If you enjoyed the show, please consider subscribing and leaving a review. It really helps us to reach new listeners. Until then, stay curious and keep exploring.